everyone, to our statistics seminar. So this is the second to last one, so we still have one more. I sent you a message. 2 weeks from now, we're going to have our last one. So today we have the pleasure to have Professor Hans-Georg Müller. He's a professor in the Department of Statistics at the University of California, Davis. He has served as chair of the Department of Statistics, founding chair of the graduate program in biostatistics, and has been engaged in various biomedical research consortia aiming to quantify brain and neurocognitive development from brain image data with support from NIH, NSF, and the Melinda Gates Foundation. His contributions to statistics include early work on smoothing methods for nonparametric regression, methodology for growth curves and change points, sim parametrics, and structure modeling in regression. So he has developed a major effort to develop theoretical and methodological foundations for functional data analysis, notably functional principal component analysis, empirical dynamics, and several other directions. So without further ado, Hans, the floor is yours. And so we're going to have 50 minutes for the talks and 10 minutes for questions.
Thank you, Carlos, for the introduction. I'm talking about distance profiles and conformal inference today. This is joint work with Hang-Su, who is a postdoc currently at UC Davis. And let me first talk about object data, because the talk is based on two things. One is object data, the other one is conformal inference. And so I will try to give a very brief survey of each topic. First of all, the object data. Okay, so the idea is here we have random objects as our data, which are complex data that take values in a metric space.
Sorry, I'm interrupting. Are we supposed to see the screen on Zoom?
Oh, we forgot about that. Sorry about that. So,
thank you.
Let's just open Zoom.
Yeah, sure, go ahead.
Right. Can you see the screen now?
Yes, thank you.
All right.
Well, let's get out of this. Okay, thanks. Okay, so random objects are data that take values in a metric space. And there's also a probability measure. So sometimes we'll refer to this as a metric measure space. Well known in mathematics, but less so in statistics. So what we are talking about are samples of random objects. That means you have samples of metric space valued data. And these data are commonly observed, but there is not much in terms of theory or methodology. So the goal is to create statistical and interpretable methodology for such random objects and supporting theory as much as possible. I will talk briefly about exploring samples of random objects with a method that we have developed called distance profiles. Then since conformal inference is about regression, I'll talk about briefly Fréchet regression, which is for object data as responses, and then conformal inference. So we need some restrictions on the metric space. First of all, it has to be separable. Secondly, all the theory is based on empirical processes. And so we need some entropy conditions. I will not give any details on this. You can read it in our preprint, what exactly is needed on this. Okay, so let me give you some examples of random objects. These include usual data, that means scalars and vectors, but they go far beyond those objects. Namely, we can have random functions. These are data in infinite dimensional Hilbert space. These are called functional data, and the area is called functional data analysis to deal with such data. This is still closer to the usual statistics than the general objects because we still have a linear structure. That means there's a vector space here. We have an inner product. We can do projections. And we have the concept of multivariate analysis and linear operators at our disposal. Singh and Eubank is a good source for the linear operator theory, specifically for functional data. However, this is still a very special case. In general, we do not have linear operations. So data would be, a next class of data are those on finite dimensional Riemannian manifolds. For example, spheres is very common. This area has been well developed. It's called geometric statistics. And usually you do a local linearization because you can put a tangent space, a tangent bundle on your manifold, and you can linearize locally, which is good enough for many approaches. So there is still a notion of linearity here. But now we go to more general cases like random distributions, in which case the linearity is further removed. So here we would have samples of distributions. So each of our objects is a distribution. So that's my data point. Of course, there are some additional issues I'm not going into because the distribution is not known. I have usually just data points sampled from the distribution, so I have to estimate it somehow. Not going on this. Anyway, this field is called distributional data analysis, and Peterson 22 has a nice review article. Another class are symmetric positive matrices and surfaces, where you can have many metrics. There are still metrics coming up, like a metric by Jung and Schwarzman 2015, and then Lin 2019, Cholesky based metrics. So there are many metrics for such spaces. And then the next case is networks, which can be represented as graph Laplacians, or in other ways, I have worked myself on graph Laplacian in network regression. So the idea is your network is your sample object. You have hit the whole network and you have many of them. And then you want to regress those networks on some predictor. That's called network regression. This is an area where recently there are more people publishing. Finally, trees are another class. So there are phylogenetic trees with the so-called BHV metric, which we were able to, which is known to be a Hadamard space. That means non-positively curved. That's a special class of metric spaces, which are advantageous in some way. And it also satisfies the entropy conditions we need. We showed this in 21. So that's included in the theory. So the idea is to generate, as I mentioned, a statistical methodology, quantiles, there's regression, variance, inference, whatever you want, for such random objects, tentatively called metric statistics. So the starting point for all of this is a sample of random objects. So you have a sample xi, which are in the metric space. I call the space omega here. And the first job you have when you have such data is to select a metric. Unfortunately, we don't know how to do this, so there is no statistical method really available that tells us how we should select a metric that's suitable. So we go by criteria like suitability for statistical analysis, interpretability, also human perception, what's similar or not similar. Okay, so you can show people some objects and say, are they similar or not similar? And then try to find a metric that mimics this. Because you have usually many metrics available. Another thing is mathematical convenience. We always want a metric of so-called negative type. If you want to know what this is, please read a paper. This is complicated concept, but we need this. And most metrics in spaces that we care about do satisfy this. So it's not really a big restriction, but we need it. So the key challenge for this whole area is that you do not have linear operations, no addition, no subtraction, no scalar multiplication, no inner product. So a lot of the classical statistics breaks down, is not possible to use, and therefore it makes this field interesting because you have to reinvent basic notions. Okay, so brain connectivity is one example. I have worked quite a bit on brain imaging, which generates data of interest. So for each subject, you record, for example, a fMRI bolt signal for each region of the brain. And then you correlate those signals by some correlation measure. You got a correlation matrix which you convert in the network, as neuroscientists like to do. And then you got for each subject a network, and you have maybe 200 subjects in your study. You want to know many things. For example, is the network of a person normal, or is it an outlier? Secondly, how can we predict networks based on patient characteristics such as Alzheimer's score or age and things like this? I work specifically with children's data where we have such networks and we have characteristics of the child we want to know. Given those things, is it an outlying child or is it in normal development? Okay, so these are all things where the complex object is one element of your sample. Another class I mentioned already are these distributional data. So here age at death distributions for females and males in Eastern European countries. So these are densities which show the distribution of age at death. So you see the age here, right? And this is the density. This is 1990 red, 1993 blue for males and for females separately. And this is for Eastern European countries. The Soviet Union broke down between these years. There's a breakdown. And what you can see from this already optically is that males were much more affected than females because their age distribution moved left big time, which is bad, right? That means they die at earlier ages. For females, also moved a little left, but much less. So they were less affected. That's already optically quite clear. So these are distributional data. I want to mention this as an example. Each distribution is an object in my sample. Okay, so the first thing we need is a mean. We want to do data analysis. For that, Frechet 1948 had the idea to define a new mean, which is just using a metric, namely the minimizer, the object that minimizes the square distances to all objects in your data set. So we take the outmean of this expected distance squared. Remember, there's a probability measure. The expectation is with respect to the underlying probability measure. Then we have an empirical version. These things may not be unique. Generally, there is no uniqueness, so mu plus is a set. But in some cases, like Hadamard space and other conditions, we can get unique minimizers. So this is the new notion of mean. It's not new. It's 100 years, not quite, but 80 years old. Here an example of Frechet means for distributional data. So the metric is key here, what you get. So what's very popular recently is the Wasserstein metric. For one-dimensional distribution, it's quite easy. It's just the L2 metric of the quantile functions. So if capital F and G are the distribution functions of my two distributions, and the densities are small f, small g, which I assume to exist, then we have a choice of two metrics. We can take the Wasserstein metric above, in the formula above, or we can take the Euclidean metric for the densities. I just take the L2 metric for the densities. Okay, and then what you get for the Frechet mean. In the left-hand side, the Euclidean mean. That means just cross-sectional mean of all these densities is a simulation. The light gray curves are the densities that we are shifted left and right, and they also have different variances. All Gaussians, but shifted and with different variances. So these are my random sample of distribution. If I want a mean, the Euclidean gives me this, which doesn't represent any of those gray curves, while the Wasserstein gives me this, which is actually very representative of the sample. That shows in a nutshell why Wasserstein is so popular in one dimension, at least. Okay, so the Frechet mean of the Wasserstein is useful, interpretable. The Frechet mean of the Euclidean, which is just the usual cross-sectional mean of the densities here, is not. It's actually a very nonsensical and useless mean. So you can see here the metric matters big time. Now, the next step, once we have the mean, is the conditional mean, right? So we want to think about what should be a conditional mean if I have predictors for my objects. So X here is RP, random vector. Y is an object. So I have pairs X, Y. And I want to talk about the conditional mean. So again, like the Fresnel mean, I define it as a minimizer of the square distances, but now conditionally on the predictor. So this is a straightforward extension of the Fresnel mean. However, if you want to do data analysis, you have to implement the conditional mean. As you know, in classical statistics, the conditional mean is implemented by any regression model that you propose, right? Regression is a regression model is a implementation of a conditional mean. And so it is here, we need to find the implementation. What we do here is we take regression weights S, we take the weights S here, and then we minimize the square distance of Y with the omega element that we want to minimizing omega in our space, such that the square distance times the weight is minimized. So this, this approach is derived from the Euclidean metric, where this is exactly what you do when you do linear regression or local linear regression. I will show in the next slide. So what we can do here is we can prove uniform convergence, for example, of this method, and then you can do also random object time warping models. I'm not going to talk more about this part. Here's the detail. So you have random pairs X, Y. Remember, X is in RP, Y is in your object space. They have some sort of a joint distribution. And you may know, at least PhD, more advanced PhD students, that the mean here, the mean can be written as the element that minimizes the square distance, like the Fresnel mean, except here the distance is just the difference because we are in Euclidean case. And similar, the conditional mean minimizes the conditional square difference, right? So if we do a linear regression, we put in a special model for the conditional mean, which is the classic linear model. And if you use the squared error loss, you can equivalently express this model in the following way, that at x, small x, you take the minimizing element of the expected value of the weighted square difference, where the weight function comes from this linear regression. So, sorry. This is totally equivalent. And so you can see that how we extend this, because now here you have a difference squared. So I can use D in the special case instead of the difference. This is a Euclidean metric, and I just replace it by, I replace this by a general metric, that's all. The weight function comes from the linear regression. So we call this the global Fresnel regression. So the definition is simply here. So it's a strict extension of the linear model to metric spaces. So if you indeed have a Euclidean response, you get back the linear regression. It's a special case of the channel of this channel framework. So it's a strict extension of linear regression to the metric space valued response. And you can also use a local weight function for this. Alternatively. Okay, then there is this is population model. You want to estimate things, so you plug in empirical distributions of your data, xi, yi. And you can then show that these estimators will satisfy certain convergence results. This depends on the entropy conditions that you pose on your space, on the curvature of the loss function around its minimizer, and some other regularity conditions. Not going to give any details. But we will use this Fresnel regression for the conformal approach that I come to next. Not yet. First of all, we need to explore the data, or we want to explore the data more. So one tool that is very useful are distance profiles, which are defined as CDFs of the distribution around a fixed element omega. So you choose a fixed point in your space. You choose a fixed point in your space. You take a radius r around it and you look how much mass falls into the ball. And you do this while r is varying. There are some other, some other people had the same idea at the same time, actually. So this seems to be a pretty pervasive construction. What happens is these f omega are now a family of one-dimensional distributions, which are indexed by your starting point omega, the center of the sphere, of the ball. And you can do this now for all omega, right? And then you do an empirical version. Again, you just plug in your data. So here, a little illustration of this. This is a case where we still have a Euclidean response, which is a two-dimensional normal distribution. So it's not really object. To illustrate this concept of profile, distance profile. So here is the center point. This is the distribution. And this is the density which belongs to it. If you go further out, away from the center, you get to the purple case. The distribution has moved to the right because nearby there are not so many points. In order to catch more points, you need to increase the window, the radius. Oops. So you catch fewer points. And if you go even further, you catch even fewer points nearby. So the CDF rises in a flatter way, and the density moves here from left to right, as you can see. So here again, I don't know whether that works. Let's see. Yeah. So here the point is moving out. It's the same distribution. It's just animation. The point moves out. The density, which is, this is the density moves to the right, and the CDF gets flatter and also moves to the right, right? So that's the idea of the distance profile. So each point gets a distribution assigned and then a density. We assume densities exist here. Okay, now comes the optimal transport, because you have now a distribution at each point of your metric space. And what you want to do is you want to transport them to each other. So we transport a distance profile at omega, which is called f omega here, to one that's centered at x for any pair. Okay, and the transport is very simple. It's just a probability transform, which is this, which you can write as minimizing the transport here. This is just a formality. I'm not going to talk to give the details on this right now. The point is that I can define a push forward map to map one distribution onto another, where on the real line, let's say we are on a bounded interval, you push the mass that you have from f omega, your starting point, forward to the mass you will have at fx, another distance profile. So for the same case I showed before, this is an illustration. What happens is, this is the central point, if you remember, the red one is right at the center. If I push this forward to the purple or to the blue, I have a transport here. Oops. I have a transport here where the interval 0 to 10 is moved always to the right. So any point here moves to the right. So up means move to the right. So you have mass here that corresponds to your starting distribution, which is the most central one, the distance profile. I move to the most extreme one to the right. I move most, and then to the purple one, which is a little extreme, but not totally extreme, moving right along the purple transport curve, okay? So you can see these transports are all positive. That means my initial point has to be very central, because I need to move to the right to get to the others. If I take the purple one, you can see that if I go to blue, I have to move to the right. If I go to red, I have to move to the left, right? Because this one, in order to get to this red one, I have to move mass left. From here, I have to move mass right. If I start at the blue one, I move mass only left. Let me know if any questions. And this simple scheme can be used to define transport rings. They are actually continuous, so ring may not be the optimal name, but we call it transport ranks, which quantify the centrality of each point. You just look now at the expected transport. You start at omega and look, does it predominantly have to transport to the right or to the left? And if it predominantly to the right, then this point is more central, right? So if predominantly to the left, it's less central. So this X-pit function is used just to make it between 0 and 1, also known as softmax. Okay, so again, you plug in empiricals and you got estimates. Question? No. The key is that these transport ranks are unique in the sense that they characterize the distribution. If you have a space of negative type, which we want, in this case, strong negative type, which is even a little stronger, then the two underlying measures are the same if and only if the ranks for all omega are the same. That can be shown, and that means those ranks, which we construct here, characterize the underlying distribution totally. So this is a very useful basis for further statistical analysis. Then there's some results on large sample behavior of such empirical transport ranks. For example, you can think about a process that's defined in space omega and t. So it's in a product space where omega is your start point of the balls where you collect the mass of the distance profiles minus the true one. So this is the estimate minus true one squared, and you got a Gaussian limit with specified covariance. And you can also show that the rank estimates can be uniformly consistent over omega. So this is kind of, this is the first part of my talk. The second part now tries to connect what I just said to conformal inference. So the idea is this: we have a Fréchet regression I mentioned, which is a regression, if you remember, where X, the predictor is in RP, the response is metric space object. That's my regression I have. We did this in previous work. Now, what you want is not just a point estimation, the point prediction. If you have a new X, you want to know a prediction in the wall. You want to know how precise is my prediction of a new point. And that's where the conformal inference comes in. So that's the natural next step. Basically, it tells you how good is your prediction. If you have very, very wide interval of prediction in the wall, you are not so good. Okay, so conformal prediction in general is a non-parametric method to obtain prediction reached in a regression setting. That would be a very general statement. If you want to learn more about it, read by Schaeffer and Walk, which basically has the basic elements for this method assembled. So the idea is we have data, n data, xi to x, yi equal 1 to n, and now we have a new data point, which we call xn plus 1, and a new response yn plus 1, which we have maybe not observed. What we want is a prediction region where the new response most likely will fall, okay, into that region. And there are two criteria for this. One is called marginal validity. That means I want a region C hat, which I construct, such that the new point falls into the region with probability at least 1 minus alpha. This one is overall for all new points. So it's not actually optimal because it averages out good regions and bad regions. Since you don't know here what the new point is, the xn plus 1, your new predictor level is not used here. So this averages over all new predictors. Therefore, it's not so good. What you really want is something where you know the predictor level and you want to show that you have a region where, in fact, your new data point falls into a predictor set where you know what your predictor is, okay? That's called conditional validity. That's the harder but much more valuable property. So the conformal inference is based on a score function, which determines the size and shape of the prediction regions. So the first method and oldest method is the residual score. So you have a mean regression, right? You have a regression. So there is some estimate of or there's some true regression function EY given X. You don't know what it is. You have a method to estimate it. You plug in your estimate, G hat, and the key is that we don't care what method you use. If you use a bad method, your prediction region just will be very big. If you use a good method, the prediction region will be small. We do not need to know what method you use for this. This is the key why this method is so successful. So you may use a linear regression when the data is highly nonlinear. Doesn't matter, it still works. You still get a right region, but interval, but it will be huge because you have the wrong regression model. So we don't need to know what the regression is. That's a key why this method is successful. Okay, so you can use anything which you have in mind. Hopefully you have something good. If not, then your region will be just very big, but it's still valid. Okay, so there is also a standardized version of this residual score. So here we just take the absolute value of the residual. Here we take the absolute value divided by sigma hat, but this is an estimate of the variance at predictor level X if we have one. And recently there are other scores, for scalar responses which have advantages in one way or other. There's a Chernotzukov DCP score and it's Bicky HPD score. I'm not going to give a lot of details on this, otherwise I will not be able to finish the talk. So this would be the HPD is considered by some people a gold standard currently. Okay, so now why does the method work? The key again is the split conformal algorithm, which means you randomly split your data into a training set and a calibration set. You train your model, the estimation of the mean function, which may be wrongly specified. We don't care, as I said. You train your model on this training set, and then you evaluate the conformity scores on the calibration set. And then if you take, for example, the absolute value of the residuals, you just take the upper alpha mass out. So you take the alpha or 1 minus alpha quantile and take the rest to define your prediction region. Okay, so essentially because of this calibration set, the residuals, if you have a bad mean, just get bigger. But if you take the quantile, alpha quantile out, you still get a valid construction of your set. That's the secret of this method, as I understand it. Okay, so the general assumption is that you have IID data, but this can be weakened in many settings. Some people make a big deal that you only need ergodicity or something weaker. Depends what kind of data you have, if you have some dependency. I assume IID for what follows. What we know is the conformal framework is distribution free. We don't know what's the underlying distribution of the data. We also don't know what a true regression model is. In that sense, it's model agnostic. And it has computational efficiency because the split conformal approach is very fast. You only need to train them on once. Marginal coverage is guaranteed by the construction, but not the conditional coverage. That's the sort of the gold standard that's harder to achieve. So what you want is conditional validity, and you want small prediction sets on top of that, because you can have a dumb method which constructs very big prediction intervals or will be correct, but the intervals are too big. It's like confidence intervals. You can always make them bigger. You got the right coverage, but you get inefficient intervals because they are too large. You could do with smaller intervals. That's what you want, right? So these are the two main goals that need to be achieved. Here an example. This is taken from Ching Lei's paper 2018, who is a really expert on conformal, which I'm not. And he shows on the left, the pink data is when you use the residual, absolute value of residual as your scores. And on average, you are right, but since the data is heteroscedastic, you are not right on the right, and you miss a lot of points there. On the left, you are too big, right? You should be smaller. The right one, the blue one, remedies that. This prediction region is much better. Why? Because it's using the standardized residual score. So you divide by an estimate of variance. So this is nonlinear. So they use a nonlinear, non-parametric smoothing method to obtain the fit, which is the red curve in the middle. But this fit is not relevant for the method to work, okay? I mean, you don't need to have a good fit. They obviously, I assume they have a good fit. Okay, so now we come to the marriage of the two lines. I talk about conformal, I talk about object data. Where do they meet? That's kind of the last part here. So I consider data where X is a vector predictor and Y is an object response now. So we are now in a, oh, I write M here, sorry, it was omega before. We are now in a setting where the response is in metric space, right? So think about network or distribution. And still we want now a prediction set that achieves hopefully asymptotic conditional validity, which is this here. So we can actually not prove finite at this point, finite conditional validity, only asymptotic, which is reflected by this small OP term here. So you are 1 minus alpha, but there's some error that goes to 0 in terms of your coverage. So again, we can, if we do this in our project, we start with the residual score because that's how conformal started. So what would be the residual score here? Well, for the mean, we took a Fréchet regression. Either we use local version, which is an extension of local squares, smoothing, or we use the global version, which is an extension of linear model, right? So you use a version that you think is the right one for M hat plus. So that's my fitted regression, which is an object. And the observed object is Y. So the residual squared is just the distance squared, right? Before it was y minus y hat absolute. Now it's a distance between the Fréchet regression fit and the observed value. But this turned out not so great because if you use this here, I actually can do this also without a predictor. Okay, so this is an example where I don't have really a predictor, but I can use the same method. So you can see here that so that the Fréchet mean is the Fréchet regression is just a mean, the Fréchet mean. So you can see here that the region we construct with the residual score is correct. It has the right coverage, but if I have a mixture of two-dimensional Gaussians, again, this is actually an example where the data is two-dimensional Gaussian, so it's Euclidean, it's not really a general object. You can see this prediction region is way too big, it's highly inefficient because I have actually two clusters and it cannot separate them. That's the problem for any residual score. The residual score just doesn't work very well if I have any clustering like here. So we have to do something else. Of course, we already had the idea of the distance profile. And it was very natural to connect to that. So the first step is we extend the distance profile to a conditional version. Before, when I introduced it, I just have one metric space. Now I have predictor X. So I do a conditional distance profile. That's the definition here, is very natural. Oops. And then we use average transport costs for those conditional profiles. It turned out that the best way is to do the Wasserstein 1 cost rather than the Wasserstein 2, which I showed before. So the Wasserstein 1 is this distance. It can be written either between CDF or between quantile function, because in Wasserstein 1, when you take the L1 distance, which this is between the cumulative distribution functions of those distance profiles, if you take the Wasserstein 1 under mild conditions, this is the same as the L1 distance of the quantile functions. Okay, so quantile function L1 distance is the same as L1 distance of the CDFs. If you make a graph of the quantile and of the CDF, you can see this very easily. Under mild regularity conditions. So I write it here in terms of cumulative distribution because these are our distance profiles, but I could also use the inverse. That means a one-time function. So this is the conditional profile average transport cost called CPC. Again, conditional on X. And so this quantifies the average transport cost in terms now of the one Wasserstein, not two Wasserstein, which I had before, moving from f omega x to fyx. Fyx is a random observation in my conditional distribution, f omega x fixed, right? And so a small value of this means that I have mass, a lot of mass nearby because the transport cost is low. So there must be many masses nearby. So the transport to the average is not costing me that much. Okay, so now the choice of the score function. Of course, we already have this conditional profile average transport cost. We want conditional validity. As I mentioned before, that's very important. We want to handle clusters or multimodal distributions. And we want small prediction sets. These are sort of the key targets that you have. And then you need to find a score function that works for this. And what we found is that the CDF of the conditional profile average transport cost, which is defined here, is actually doing nearly all of this. So we take the CDF of the transport cost. So this is a little complicated. I write here capital Y, right? But the cost here starts at Y. This is your starting point. And you transport to all Y prime in your conditional distribution. So you have actually pairs Y and Y prime. They are independent from the same conditional distribution. And this is the transport cost transporting from Y to Y prime. A second realization of the response at X, at the predictor level. And so here we look at the probability that this cost is smaller or equal to Z. The transport from a random Y to another Y prime, a new observation. So that gives me the score S, which we call the condition profile score. And this score has a property that as any useful score function, it's uniform. When I take this score function, it's uniformly distributed regardless of the value of xi, which is on which I condition. That's my predictor level. Now, how do I estimate it? This is quite complicated. We have to do kernel estimation or local linear, something like this, because you need to stay close to your predictor level. So for now, I do one-dimensional case only for the predictor. Okay, X is R1. So first of all, I find the conditional distribution functions for all distance profiles. So this is a standard way to estimate conditional distribution functions. Has been proposed in the around 1980. It's very old method. So there's nothing new about this part here, this F hat. Then I got the estimated conditional profiles. After that, then I need the estimated transport costs, right? One Wasserstein transport costs. That's codified by this J. And again, this method is using the local linear estimation paradigm to get the conditional cost at any point omega, starting point. And finally, I wanted CDF of this to get to my score. So again, I use a CDF approach like I did here, but for different indicator function. Again, local linear kernel method. So you have 3 steps that makes the theory a bit tedious. And finally, you apply again the split conformal algorithm. So you have a training set, you have a calibration set, and you obtain your set by taking again the alpha quantile to obtain the region that you want. But one problem, if you look here at output, is this. I can't visualize this region. I can't even analytically obtain it because we are in a potentially super complex metric space. So the only way you really can do it is you have a Y. You want to know, is it in or out of my prediction set? So what you do is you have to run the algorithm to see whether it's in or out. So you for this Y, you calculate this quantity and you find out it's smaller or larger than Q hat alpha. In practice, it works, but it could be tedious when you implement it because you are, let's say you are in network space, you have to check for any network that you have in mind, is it in or out of prediction set? We have no analytical formula that delineates a subspace of this metric space at this point. Anyway, now there are many auxiliary results. I skip all of them. The main theorem, or one of the main theorems, is that if you have a certain covering number of your metric space, n, which tells you how many small balls you need to cover the whole space, then I can get a uniform result with my estimate for the cost function, the condition cost function I mentioned, and you got certain rate of convergence. And in some spaces, I cannot have this. So the result A is for multivariate data and also functional data. I have a result of type A, but for Wasserstein, for example, I only have a result of type B because this metric condition is not satisfied in Wasserstein space when my distributions are the objects and I use a Wasserstein metric, which is different, by the way, from the Wasserstein metric I use in my method. They are not the same, right? So I could have objects that are distributions with Wasserstein metric. Then I have to go on part B, which has a slightly slower rate of convergence. But anyway, the key is that under regularity assumptions, we can actually show that we have the conditional validity asymptotically. That's a key result of the whole thing. So it gives valid prediction region in a complex setting. So we have the asymptotic conditional validity. And this can be difficult even in simpler scenarios like real responses. Well, okay, let me quickly go to my application. There's a case to extend to multivariate predictors. I will not talk about it in detail. We use a single index Fréchet regression, that means dimension reduction, that we had already published before for this. Yeah, if you want to see that detail, look at the preprint archive here. About the whole thing, not just this part when we have multivariate predictors. Here, some simulations with this new approach. So the tree space on the left, so you have the red points outside and the blue points inside your confidence region. It's just a very simple tree. In the middle, we have data on a sphere S2. Now you can see that we get much smaller region with this new approach as compared to the previous one, where you have huge region and cannot discriminate the clusters. So this new method actually does allow you to determine clusters. And here a distributional case where I have difficulty with the visualization. So I can only show outlying ones, which are red, they are not in a prediction region, and blue ones, which are inside. There is unfortunately no good way to show the boundary of this region because in this case, you have distributions represented as densities. Then we have New York taxi data, which are networks. Maybe I skip those, right? I'm low on time. Yeah, okay. I skip this one. Instead, let me just end up with, so the network, I have a network example, but it takes me more time to explain it. Let me just, as last example, give the states, US states energy data. That's energy consumption sources. 3 categories of sources: coal, petroleum, wood, and fossils. Natural gas is second category, and the third one is green sources, by and large. So the thing is that these data are all publicly available, and they are available for every year, for every state of the US. And so you can take this as proportions, u, v, and w. They add up to 1 because these are fractions of which energy comes from. So if we take the square root, we are on the sphere as 2, which is the Riemannian regular sphere. Okay, and here is my last slide. It shows how our prediction region that we concern with this complex method moves from 1990 to 2021. So this is just a quadrant of the sphere where the data are positive. Oops, sorry. Data are positive, right? Because we have positive and the square roots, the sum of the square root squared is 1. That's why we are on the positive quadrant of a sphere. And the prediction region moves from 1990 to 2021. What you can see, it moves from fossil. The fossil is high here and is low here. It's a little bit complicated, this axis. Gas is low here, high here. And the renewable is low here and high here. So what you can see, if you look carefully, the renewable is actually increasing in the prediction region. And that gas is increasing big time because here the gas is including 0, but it doesn't do any more here. So gas is much higher predicted. And fossil, which are high here, are reduced as well because you can see here there are a lot of data at fossil 1 which are gone here. So we see what we expect. A move away from fossil towards gas and towards renewable. The move towards renewable is a little bit weaker than the one towards gas. So that's my last slide. If you want to read more, then read, there are 2 papers I was actually presenting to some extent. The first one is the Conformal Inference paper, and the second one is Metric Statistics. It was already published. Yeah, I showed this picture because you see the reflection conforms with the actual model. So that's a conformal idea. Yeah.
So we have time for one or two questions.
And that's kind of a silly question. When you embed the data on the sphere, is there any reason that this is more naturally motivated than just leaving it on the simplex like it was before, or is it just to illustrate?
Yeah, it's to illustrate, and when you have a simplex, there are certain difficulties. For example, you want to you need to stay away from the boundary, and you need to be able to define a reasonable distance. On the simplex, it's pretty contrived to get a distance. So on the it's just a Riemannian, and also the sphere is kind of a natural metric space for us. It ties to the whole system, but in fact, there are different metrics and spaces used for compositional data. It's not just spherical. There's an Atkinson transformation, which I don't know whether you know about this. So there are different ways to represent such compositional data. Some people try to move it into a linear space, but it's not totally successful because that map is not reversible. Yeah. So there are different ways. You are right. It could be done differently. Absolutely. But you know, that's the general thing here is we never know what should be the metric. And in some cases, we don't know the space. I use here sphere, but you could use a different space. Even if the space is clear like distribution, I don't know what should be my metric. Okay, so you have seen that the Wasserstein 2 metric is useful. It gives a very high interpretability, at least in one dimension. For statistical analysis, that's why it has been very popular. In my case, it's already much more complicated. I talk only about one-dimensional transports and Wasserstein. And networks, also many metrics available. And your result depends on your metric. If I change the metric, I get different region and everything. So this is a problem that has not been addressed. In the Euclidean case, most people just use the Euclidean metric, but even that is not so clear you should use it. Because there you could use a different metric. We don't know whether Euclidean metric is the right way in all cases. The metric selection is a thorny problem, and I don't think it has a very well-founded solution at this point.
So trying to think about that problem precisely. I mean, I tend to think about the choice of the metric in some sense as being similar to the choice of distributional assumptions that you make in more statistical setting. And in the Euclidean case, you can usually map things around, right? So Euclidean roughly corresponds to normality.
Yeah.
Absolute value corresponds to roughly Laplace or double exponential. So is there a way to think in those terms when you start moving into random optics?
Well, only, I mean, are you talking about linearization or?
Well,
Not
what I'm trying to think is there a way to think about the problem of choosing the right metric in some way as being similar to. So parametric modeling, you make an assumption about what is the parametric model from which your data is coming. So I'm just trying to see whether it's an analogy between that choice and the choice of the metric, and whether, you know, when you're doing 1D modeling, whether something.
Yeah, okay, I see your point. Yeah, yeah. But the problem is we don't have a Gaussian distribution on our spaces. There's no such thing. In fact, it would be very difficult to come up with any distribution. What we know is densities typically don't exist. That's already the case in Hilbert space. Only in if you take a quotient with respect to another Gaussian measure, you can define even a density. You cannot do it with regard to Lebesgue measure, even in a Hilbert space, not possible. And so in those spaces, we are even sort of much less defined than Hilbert space. And so in Hilbert space, I can define a Gaussian distribution, but in the general space, not. There is no distribution that is actually feasible. That's why this conformal method is good in the sense it's completely distribution free. We cannot make, and we could not, we don't even have a distribution assumption. So it's as good that we don't need it for the conformal because you don't need it, right? Even if you have a real response where you could have one. In that regard, I think the methodology here fits nicely together in the sense that none of this is related to any distribution that I need to specify. Yeah, so I mean, regarding metric, if I'm on a sphere, I think there will be very few alternatives to the geodesics, the Riemannian metric on a sphere, or for Riemannian manifold. But if you are in distribution space, it's much more murky. I mean, even in the Wasserstein class, I have Wasserstein P. So you can take Wasserstein 1, which I use in the transport for the cost function. But many people prefer, because of the interpretability, Wasserstein 2. But you can also have Wasserstein P. So even that one is not clear which one should you use. If you do computer science, again, where they also use Wasserstein, they use usually Wasserstein 1 for computational is, but it's really not clear what we should use. So even in the Wasserstein class, it's not clear. Not to speak of that I go away. You know, there are 100 different metrics, maybe 1,000 for distributions. We really don't know which one we should use. But the picture I showed before probably showed that we should not use the Euclidean of the density L2. That's a bad one. But generally speaking, we don't know. The metric selection is a problem that maybe cannot be solved. I don't know. At this point, everybody who does such data analysis just chooses whatever is their metric they like and which they can do the mathematics. That's another issue. Maybe you can do it or maybe you cannot.